Thanks a lot. So this conference has always been memorable for me. This is my third time here in 3 years, and every time I've come here, a lot has changed personally and professionally in my life. So first time we were here, we were a small startup getting started, from Singapore. Last year we were sponsors, and this year, as I speak in front of you, as you can see, we got acquired by CA Technologies. We're part of the CA Veracode business unit. But what I didn't realize last year was what would change personally is as I speak today, I didn't realize my 1.5-year-old son would be watching the live stream from home. So, Anhad, if you are looking at me, it's hi from dad. All right. That said, let's get started. So, this is the outline for my talk today. At first, I would like to describe a bit about the problem space. So, why is it that we are interested in, third-party components or open source libraries? Then I'll talk about what do I mean by unidentified security issues. So if you look at the title, I do not use the word like finding or discovering vulnerabilities. So this talk is not about finding new vulnerabilities. It's about identifying those which are known but are hard to identify because we have to sift through a lot of data. Then we'll talk about how machine learning can help in this respect. And then I'll share with you the details of the machine learning work which we have done at Veracode and talk about briefly the results we have. So let's get started. If you look at the growth in third-party components and libraries over the last 5 years, it's been truly exponential. So I think this data is from till 2017. So you can clearly see there are over 1 million different unique libraries or components. So this is summed over from various sources like NPM, JS, Ruby Gems, Maven Central, Composer, PyPy, etc. Right? And if you extrapolate a little bit, and consider all the unique versions of the components, it's really staggering to see, in the next 10 years, how many libraries or how many components we can have. It's also compounded by the fact in certain languages, like say, example, Golang, every single commit that someone makes into a repository can be considered a unique version because you could include that in your project, right? So this has been happening. If you look at individually in applications, the complexity of the applications themselves have exploded. So this is data we collected from customer scans at SourceClear. So if you look at, on average, in one Java project, if you add one direct library, that in turn depends on 4 others, right? And in certain ecosystems, there is a difference. For example, in JavaScript, this problem is really compounded, as you probably know. So every single JavaScript library you add to Node.js project, on average, 9 others are added, right? Now, if you're thinking from the perspective of security, your attack surface is increased every time you add a single library. The way we build software has changed. So today, if you start a typical application or a typical web app, you start off with some basic open source code. So you have some frameworks, you have the languages, you have runtimes. Then you write very little custom code or business logic or first-party code. And then you include a bunch of dependencies or components through which you assemble your application, right? So if you're thinking in terms of security, the attack surface of your application, more than 90% actually resides in third-party code, most of which is open source, compared to first-party code that you own or you wrote yourself. And very recently, you must have heard about the latest issue in Apache Struts, which is another very popular Java library. Last year, an issue in Apache Struts, the remote code execution was responsible for the largest data breach in history at Equifax, right? So this is a real problem. And the problem is that developers are building applications using code which they don't own and control. So how can we help them identify the vulnerabilities or issues that exist in those applications, right? So now I'll try to talk about what I mean by unidentified issues. So if you think about this problem and you have an application and you included a library and you want to know whether there's an existing issue that is there in the library. So there are some places you would go ahead and try and find these issues, right? So you have the National Vulnerabilities Database, which publishes CVEs. You have several vendors, they publish their own adversaries. So they would have okay, I'm Spring or I'm an Apache project. These are the vulnerabilities I fixed in this version. Please go ahead and upgrade. Or there are certain mailing lists you can join, bug tracks, full disclosure, etc. And you would know the known vulnerabilities, right? However, how often do you see a JavaScript vulnerability disclosed through NVD, right? So certain languages and certain ecosystems and open source communities do not follow, for whatever reason, the process that has been used in the past to disclose these issues. They go ahead, fix it silently, and then move on. So many issues are often not reported or publicly mentioned or disclosed in this manner. Even if those issues are publicly disclosed, it is often possible to identify them weeks in advance if you track some of the other sources of this information. So all these libraries that we talk about, most of them have source control management systems that are public, like they have their code on GitHub. You can look at the commit logs. You can look at things like, oh, I fixed this CSRF issue. You can look at bug reports. You can look at change logs, and you can look at pull requests. So at that time when we did this analysis, we looked at a collection of CVEs we had in our system, and for each one of them, we tried to figure out what was the first possible date. If we had access to that data, we would be able to identify the same issue, right? And this is the number of days, on average, a vulnerability could have been identified had we been tracking, for example, the commit messages, GitHub issues, pull requests, or the Bugzilla bug reports or JIRA tickets. So you see, it's on average between 20 to 120 days ahead of time, you could identify the same issue before it went through the CVE process and was published on NVD, right? So this gave us assurance, like there is actually, if we could figure out and solve this problem, we could help our customers identify known issues much in advance than they would be published on NVD. So with that in mind, we built a lot of tooling around this process. So I'll just describe a little bit about our internal tool called WOPR, and then I'll focus on the part which I'm going to talk about in this presentation, which is the machine learning part. So we have some crawlers which actually scan all of these things, get the latest JIRA tickets or commit messages, etc., push through a workflow engine where humans actually take a look at it. So when they look at a research item that comes through here, they're trying to figure out, given this bug report, is it likely to be related to a vulnerability or not? Or given this commit message, is it likely to be related to a vulnerability? And so on, right? So initially we started it, there was no machine learning piece. So we actually started all of this and we started manually triaging and labeling the data. And then at some point we realized, or when we had enough labeled data, we could go ahead and build our models. So that's the context in which we operate. So when we were looking to, how to do machine learning for identifying these vulnerabilities. So my background is not in machine learning. So there's a very good quote by Martin Jinkovich, who's an engineer at Google, published as part of best practice in ML rules of machine learning. So he said, like, do machine learning like the great engineer you are and not like the great machine learning expert you aren't, right? So what does it mean? So instead of actually trying to figure out the best algorithm or the best new thing or new approach that you could take, try and see how much of it you can automate and how much of it you can get away with by using things which are known and easy to understand, right? So for us, what it means is for each of these sources, we train a smart vulnerability identifier, which is for each sources, we train a separate machine learning model, which is trying to do binary classification. So for commits, it's based on the commit messages. So each message comes in, we try to do a prediction and see whether this message is related to a vulnerability or not. Same goes for all of these individual sources. Our pipeline is very simple. So we start with some training data that we have because we were doing it manually. Then we train it. We already have some fixed notion in mind of how much accuracy we want, and I'll talk about that in a minute. Once we train and test it and validate the model in production, if it meets our expectations, we will deploy it. Otherwise, we'll go back in and continue this process. Once the model is deployed in production, we continue collecting the data, so based on the predictions, and weekly we retrain the models to generate better and if there is an improvement in the process, we would actually deploy the new model. So that's kind of the overview of our pipeline. So initially, first observation we made here was that you really have to use some filtering before you can even start with machine learning. And the reason for that is, in our data set of around 2,000 so GitHub projects, there were over 3 million commits. And less than 3,000 of them were actually vulnerability related. So if you try to do machine learning with that, where you're doing binary classification, you can always have a model which gives 99% accuracy. You always say no. Any given commit, it's 99.9% accurate that it's not related to a vulnerability, right? So there is huge imbalance in the data. So in order to make our job easier, we actually filter all these security unrelated issues by using a regular expression. So this includes things like names of vulnerabilities, things like CSRF, XSS, CVE, etc. So there's a regular expression we use in order to filter it to make our job easier. We started off with the projects we had with us at that time. There were around 6,000 projects in 6 different languages. In order to ascertain the ground truth, we relied on our vulnerability researchers who were labeling this data. So this data was actually labeled by humans by looking at each item that came through and deciding whether it's related to a vulnerability or not. Right? So this is how it looked like. So even after the filtering, the data was still very imbalanced. So for example, for commits, we had 12,000 or so commits in our system. Only 1,300 of them were related to vulnerabilities, and the rest of them were not related to vulnerability. So you can see there's like a high imbalance in the data. So when you're trying to do binary classification, it's easiest to do if it's almost 50-50, because you know either it's this or that. If you have this kind of imbalance, then it's difficult to do the training. The second challenge is the natural language text that comes as part of either, bug reports or commits is very different from, say, standard English, right? So it is noisy, it's diverse, it's mixed with URLs, variable names, etc. So what it meant was we couldn't use the existing models like wet2vec, which are trained on Wikipedia text, to do our natural language processing. So we had to train our own word2vec model, which is specific for our domain. So this is kind of some of the features we eventually ended up including in our machine learning model. So if you look at commits, we looked at a variety of things, including project names or name of the contributor. But the only thing that was significant enough as a feature we found was the actual commit message itself. For bug reports, we use a variety of features, including title, description, comments, number of attachments, labels, created and edited date. For mails, we use the subject, content, and the sender information. So these are the key features. After an exploratory data analysis, we settled on these features in order to do our training. So like I mentioned, we had to train our own word2vec model. And the benefit of doing this model is that this model is trained on our own domain. So if you look at, in our model, if you try to find words which are similar to XSS, you will actually see things like CSRF, clickjacking, 1, etc. While if you train your model on natural English, XSS doesn't really mean anything. So the things that are similar to XSS, you won't see this. So we use the data set of the unfiltered 3 million commits in order to build this word2vec model. And that's the model we use for natural language processing. So you need this because in order to do machine learning, you need to convert the text which comes in commit messages into vectors. And this is one particular approach which we found was useful. We tried a variety of things, including n-grams, bag of words, etc. But the best results were when we used the self-trained word2vec model. So our first training attempts were using, basic classifiers. So we started with things like random forest. So if you know in random forest, it's a collection of trees where in training you actually look at each item and generate the forest by sampling the data set and seeing whether a feature is related to a, so this is binary classification. So you try and train and generate this trees. And when you're doing predictions, you just follow it all the way till the leaf. And if it's related, you count the number of votes and you get a confidence of like how likely it is related to a particular class. So we tried random forest, we tried SVM. So this is again another popular binary classifier. So imagine you have some data which at first looks like it's not very easy to classify. You transform it using some mathematical function called a kernel in a high dimensional vector space so that in that space, it's easy to see there's a gap and you can transform it, right? Unfortunately, when we use these individual binary classifiers, even with a lot of tuning and hyperparameter tuning, we did not get the results we wanted. So eventually, we settled for something which looks like this. If you're familiar with competitions on Kaggle and if you've done a lot of them, you'll look at, eventually a lot of teams end up with architectures which look like this, which is you try and use every possible basic classifier individually, and then you try to take the output of that, and then you try and stack that output, right? So in our model, we train at least 6 different classifiers, and each of them gives individual predictions based on the classification. And then we use the output of those classifiers and feed it into a logistic regression to give the eventual answer. So we take an ensemble of these classifiers and then use the output from each one of them. So the idea there is maybe if there is something that one of the classifier predicts well and the other doesn't, you can still figure it out because each one of them is good at a certain aspect of the data, right? And I'll share some results later on which will show, because we wanted to make sure that we validated it, and you'll see that actually using a stacked ensemble is helpful, and individual classifiers do not give that much precision. So this ended up being our sort of architecture for all of the things. So this is just for commits. The model for others also look very similar. The individual classifiers are different, and obviously the tuned parameters are very different. Right. So before I talk about the actual evaluation metrics, I want to talk about just two things, because not everybody might be familiar with precision and recall. So we use these metrics in order to evaluate our model. So think about precision. So if, for example, in the data set we have 1,000 commits, out of which 100 are related to a vulnerability, and 900 are not related to vulnerability, right? So that's the actual ground truth. Then you build your model, and then you do predictions. And what do you see? That it predicts 70 vulnerabilities, and 35 of them that it predicts as vulnerabilities are actually not vulnerabilities. So these are called true positives, which is predictions which are correct, and these are called false positive, predictions that were made but are incorrect, right? So in this case, the precision would be the amount of true positives you have over the total number. So this is 70 by 70 plus 35. So this would be the precision, right? So this is trying to tell you, based on your prediction, how likely it is that you're correct. And the recall is, out of the total number that were already there, how many were you able to find? So there were 100, but using this model, we only found 70, right? So recall is, so this means that even if you apply this model, you actually miss 30 commits which are related to vulnerability, right? So that's the precision and recall. And usually there is a trade-off to be made. And each of the models that we have, there is a metric or a confidence we can adjust in order to make that trade-off. In any case, because some of you might be having questions like, I mean, this seems very less, because I look at results that come out of ImageNet, where people do deep learning, they're always like 95% or whatever and so on, right? But keep in mind that for us, doing this as human, we had to look at 1,000 items initially. And even with these rates, we can ignore or filter 895 items. So if I had one person who was doing this work, now the task or the amount of work has been reduced by 1/10, because I only need to look at the remaining 100 commits, right? So that's kind of the important thing, for, at least from our perspective, where it helped us. So it helped us scale by adding more number of projects that we could monitor without adding more humans in the team. So this is how the actual evaluation looked like for the commits. So on this side, you have the probability for the stacked model, and then you see the precision and recall. And like I said, there is like a trade-off. So eventually the model we deployed after testing was something somewhere around here, which gives around 50 precision with almost 50 recall or something. This is to show you the fact that doing the stacking and building the ensemble is really important. So for the same recall rate, the precision is actually improved every time we use a stacked model versus only the basic classifier. So if you only use linear SVM, you get 0.22 precision. If you use the stacking, you get 0.34. Same for all of these models. So this is just to justify the case that the stacking or the ensemble is important, and without which you cannot achieve the precision you see. Right. So there are a lot of details about the actual work, including fairly detailed evaluation. So due to lack of time, I invite you to go and read our paper. We published it last year in FSC, and it talks in more detail about the results. So let me share some things from there, which is, so once we did the testing, we actually wanted to make sure once we deploy it in production and monitor it for some time. Because before we add a lot of things, we wanted to make sure that this is enough, or this is not going to miss a lot of vulnerabilities, right? So for the initial period, even after deploying the model, we continued to do labeling so that we can get these results, right? So think about it, when you publish this model in production, you are not going to look at the predictions which are negative, because that's how we get benefit from machine learning. So, but for these 3 months period, we actually still continued labeling the data so that we could generate the metrics. So based on the test, we had a precision of, the model we deployed had a precision of 0.44 and a recall rate of 6.2. We then added 3,000 new projects and then kept monitoring for 3 months. And the eventual precision and recall rate during this period was actually much higher. Now there are some reasons why it might be the case, because we maybe added projects which are very similar to existing ones or whatever. But eventually our recall and precision was quite acceptable to us, and then we stopped the monitoring. So this is the actual thing that happened during the period we observed it. So we had around 215 actual commits that were related to vulnerability, while the model was able to predict 160 out of them. and there were like 32 false positives. Right? So this is what we observed. So remember, this main goal was to actually increase the coverage. So we want to go from tracking thousands of projects to tracking tens of thousands of projects. So at the end, once we deployed all of these models, so today it helps us to track vulnerabilities at a really large scale and in low cost. So for example, we were able to increase the number of projects we track in GitHub almost 6 times. All this while, the size of the team was the same, the humans who were actually eventually doing the thing. So we still have 4 people in the team. We had 4 people 3 years ago when we started, while we track 7 or 8 times more amount of information. And it's only possible because of the machine learning. It also accelerated vulnerability identification in certain languages. So for example, Golang. So if you try and go to NVD and try to search for a Go library which has a vulnerability, you won't find that many. But when we added support for Golang, we were able to identify vulnerabilities which were fixed from commits. We added like 87 of them, and also from issues. So people reporting vulnerabilities on projects or libraries in Golang. So we identified 33 of them. So in the current system, when you're tracking bug reports, we are able to identify vulnerabilities before they are even fixed. So typically they are published on some bug report like JIRA board or on the GitHub issues page. So why do we do this, or what's the conclusion from all of this, right? So starting off with a very small team of 3 to 4 people, manually trying to triage this data. Today, so I took this screenshot earlier today, we have almost 5,800 vulnerabilities which have been curated across 10 different languages. And we still have the same number of people in the team. So the only way we could scale the team beyond the initial work was through machine learning. And that's kind of the key insight for us. And the way we evaluated our model or made trade-offs was also based on that. How much of the human time can we reduce while maintaining the same amount of recall or precision? So that's kind of the thought behind it. So as of today, we are working on improving our models. Like I said, we do retraining every week. There are some features which we did not consider. For example, for commits, we discard the most important information in the commit, that is the actual code change. So today we are working on various ways of improving that. And then hopefully next year, I'll come back and I'll tell you how that went. That's it. I think that's my last slide. So thank you for your time. We are actively hiring in Singapore. There are a lot of positions. So I would like to invite you to apply. Otherwise, thank you for your time, and I'm open for Q&A. Thanks.
Thank you, Asanka. Are there any more questions from the audience?
So, yeah, very good approach. And the question is, what's your hardware configuration? Like how many GPUs, CPUs, and so on?
So if you looked at the size of data, it's very small. And all of the training, we don't use any deep learning. So it's all done on AWS machines. I mean, they are beefy machines, but they don't have any GPU.
Okay.
It does take us some time to retrain today. So when we started, it was okay. So there are cases when we do the weekly retraining, it might take up to a day. But we haven't yet invested properly in setting up a, good infrastructure to really retrain fast.
Okay, good. Thanks.
Are there any more questions? Okay, in that case, please keep in mind that Asanka will be around for the rest of the day. So if you have any more questions, you can always ask him later. And with that, I would like to thank you again very much for your talk, Asanka. And give it up one more time, please.